This class, we will cover the electrophilic substitution on the benzene ring. And the other one is the addition reaction. Now, the main mechanism for benzene is electrophilic substitution. So there are total 4 types of reaction that benzene will run. As you can see at the right-hand corner, we do have the halogenation, nitration, alkylation, and acylation. Okay, so we want to now write the mechanism for any one. So let's start with halogenation. Okay, now for halogenation, you require chlorine gas and AlCl3 catalyst. Okay, so let me just start with the mechanism. Now, mechanism always occurs in 3 steps. Now, the first step of the mechanism is the production of the electrophile. So first, you take your catalyst. That reacts with the chlorine gas first. Now then it will break the C-cell bond heterolytically. So delta negative, delta positive. So the AlCl3 will make your chlorine gas covalent bond to break heterolytically for the temporary shift in dipole moment. Okay, I will not go into detail. And then they will form an intermediate called the AlCl4 minus. Okay, so your electrophile is the Cl plus. This is your electrophile. Okay, also known as E plus. Okay, in short. So step 1, I need to see the production of electrophile. Number 1. Number 2, bring your benzene ring, and the ring will attack the electrophile. Now, the ring inside has a high density of pi electrons that is moving. So when you are reaching electron, you will attract electrophile, which is a species that is deficient in electrons or lone pair electrons. They want to receive a lone pair of electrons. Okay, so which electron will attract lacking of electron species, which is electrophile in this case, your Cl plus. Okay, and then one of the pi bond will open up. There's 3 pi bond. One of the pi bond will open up, and therefore I put the chlorine. Okay, now we draw a half circle, okay, and a positive charge in the ring to show that the positive charge is delocalized within the ring. Why? Because a neutral benzene ring and a positive electrophile, your product form must be positive, and the positive charge is running within the ring. So the half circle inside the ring shows the delocalization of the electrons and the positive charge as well. Now, bear in mind that the half circle, all right, cannot touch the so-called antenna or the V shape of the H and Cl because that particular carbon is already saturated with 4 bonds. Okay, yeah, so this is your intermediate. Now, step 3 is to reform the ring, or maybe I continue step 3 over here. Step 3, I need to see that you reform the ring by flipping the CH covalent bond back into the ring, and therefore you will reform the ring with the chlorine now, and H plus is leave or left. Okay, so very clearly we can see that this is a substitution reaction where you put in a Cl plus electrophile over here, and then H plus is the leaving ion. So this is an electrophilic substitution. Okay, now for benzene ring, they normally undergo substitution. They would not like addition reaction in general, not preferred. Reason is because if you treat this like an alkene, when electrophilic addition is involved, right, you will open up one of the pi bond, all right? But we learned that benzene has an aromatic stabilization due to the 3-pi bond that is moving within the ring. So if you open any of the pi bond, you will disrupt the benzene's aromatic stabilization. So compounds do not like to be unstable. They like to maintain the stability. Hence, they like to keep the 3-pi bond inside the ring. So that's why the third step has to reform the third pi bond. Okay, so there are total 3 steps involved for the electrophilic substitution mechanism. Okay, so this is electrophilic substitution, but I'm using halogenation as an example. Okay, yeah. Now, can we do this another practice on a second example? Okay, so let's practice this onto a, let's say nitration. Okay, so nitration, let's look at the right-hand side corner. Nitration, you need concentrated HNO3, concentrated H2SO4 as a catalyst and run at 55 degrees Celsius. Okay, now 3 steps for the mechanism. Step 1, you need to produce the electrophile. Okay, so please memorize this equation. Okay, so who is your electrophile? I circle, this is your nitronium ion, which is your electrophile. Okay, step 1, I see the production. So if you realize step 1, we use the catalyst to produce the electrophile, be it in halogenation as well as the nitration reaction. So catalyst is help to produce the electrophile. Then only step 2, your benzene ring will react with your electrophile. So I need to see the ring. Arrow is within the ring, attacking a electrophile, which is a species that is deficient in electrons. Okay, so one rich in electron will start attracting deficient electron compounds, which is your nitronium ion in this case. Okay, so then we will open up. Now, according to my drawing on the right hand side, I put it on top. So this time I would like to put it on top here. Same thing, you have a half circle here and a positive charge in the middle. Why? Because your nitronium carries a positive, benzene is neutral. So positive and neutral will come up with a positive product. That is step 2. Now, step 3, you need to reform the ring to give the aromatic stability all over again. Okay, so we will bring our intermediate here. I need you to flip this bond back. Okay, maybe it's not that clear. Maybe I should draw a bit longer. Here, from the bond into the ring. Okay, wait, I think I, okay, I draw the bond. Okay, now can see. Okay. 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 Therefore, you get your nitronium ion and your leaving group, which is the H plus. Okay, yeah. All right. Now make sure that the covalent bond is pointing from the carbon of the ring to the nitrogen, not to the oxygen, because nitrogen is the one that's forming the covalent bond with the carbon on the ring. Okay, so this is the electrophilic substitution of nitration. But you can see there is a format in electrophilic substitution where step 1 involves the production of electrophile using the catalyst. Step 2, attacking of the ring to the electrophile. Step 3, you need to reform the ring to help them achieve stability again. Okay, yeah, so that would be the electrophilic substitution mechanism. I mean, you can also practice this onto alkylation and acylation. Okay, so for your info, alkylation here, maybe that will be your own study. Okay, maybe perhaps I'll just drag this thing down. Okay, perhaps over here you want to practice on your alkylation. I'll just give you a start off for alkylation here. Now for alkylation and your acylation, I'll give you the start off here. Now alkylation, acylation, please look at the right hand side. You have AlCl3 as catalyst and you need heat for both. Okay, I will give you step 1, which is the production of the electrophile. Then subsequently, attacking and the reformation of the ring, you all can do it independently. Okay, you use the catalyst again to react with your halogenate alkane. Then you will form the electrophile. This is your electrophile in my example, which is the ethyl group and the AlCl4 minus. Okay, then step 2, you use the ring to attack your electrophile. So in my example, electrophile here is the ethyl group. Okay, now what about the last reaction, acylation? Ring or catalyst AlCl3 react with your ethanoyl chloride. Okay, this one I open up the display formula because some of you are not familiar what is acyl chloride. Okay. So this is your electrophile. Like this. And then you continue with step 2, which is the attacking of the ring to the electrophile. And make sure step 3, you reform the ring again. And H plus must leave. All right. If you never show H plus has left, that means you did not prove that it's a substitution reaction. So when you add an electrophile in, H plus must leave. So that's why it's called electrophilic substitution. Okay. Now, there is another reaction that benzene will undergo, but it's not the main one. We call it addition. It's very similar to your alkene. Okay, now alkene, they do not have aromatic stabilization. Okay, so you just open up the pi bond. So one reaction that you have to know for benzene is they will react with hydrogen gas. Okay. Now, what do you need here? You need either a platinum or a nickel catalyst. Up to you. You choose one. Then it will open up the pi bond. Okay, cyclohexane. Okay, now obviously when you do that, you will open up the pi bond and you will not have any more any aromatic stabilization here. All right, because there's no movement of the delocalization or so-called delocalization of the pi electrons in the ring anymore. So you just destroy the aromatic stabilization and make it into a cyclohexane. This is also known as hydrogenation. Okay. All right. So therefore, for today, this section, okay, I have covered mainly on the electrophilic substitution mechanism, where it involves 3 steps. And I show you how to apply electrophilic substitution on the halogenation, nitration, and I help you kickstart your alkylation and acylation for you to practice, all right, where I start off step 1, which is the production of the electrophile, and then you subsequently follow by the attacking and the reformation of the ring. We also learned that you can actually open up the ring via hydrogenation, okay? Mechanism-wise, don't need to know for A levels, okay? You just need to know how to balance the equation and the catalyst required, which is platinum and nickel. So therefore, there are 2 types of reaction, all right? We mainly have substitution and the other one, which is addition, okay?